I will be talking about Kitaev honeycomb model, stabilizers in BCS state. This is a joint work with my postdoc Graham Cross, who has actually done most of the work which I will be talking about today. And it has contribution from Yoast. Our activities in topological quantum computation and the topological phases of matter which are taking place at the National University of Ireland at Maynooth are financially supported by the Science Foundation Ireland through the awards to Yoast Lingle and myself through two different actually grant programs, and we appreciate this support. In the following talk, I will basically address three sections. The first section will introduce story code and Kitaev honeycomb lattice model. Go through the brief introduction, quickly to the relations between both models, which are maybe well known to most of you. I will talk about vorticity symmetries and some of our results which we obtained for the Abelian case by studying these symmetries. But then I will proceed to the novel solution of the Kitaev honeycomb lattice model, which makes a use of the mapping into the spin hardcore boson system proposed originally by French group, Kai Schmidt from Germany. Then we apply Jordan-Wigner fermionization, so we build up fermionization on the spin hardcore boson system. Then we proceed towards the solution of the model in the vortex-free sector with and magnetic field. So we will be able to address not only the A phase, not only the Abelian phase, which can be and was treated in some extent perturbatively and through symmetries as in our case, but we will be able to get through the optics of stabilizer formalism into the B phase and to see the ground state of the models in both Abelian and Abelian phases as BCS states. And we will be able, in contrast to the previous works, to formulate this BCS state with an explicit vacuum, which will be given in terms of the Tory-Code stabilizers. In further development, we looked into the ground states on torus, and particularly in the ground state degeneracy in the Abelian and Abelian phase, which we know from the topological field description what it should be, and we can see that it's actually intrinsically linked to the BCS state, BCS ground states of this model from torus. The Tory code, as most of us probably know it, is a model with the spin half particles on the edges of the square lattice, which interacts through two types of four-body interactions. It's either so-called star operators, this product of four spin interactions, or placket operators, which are products of four spin interactions on plackets. The model can be transformed by unitary transformation into a different form. It's the same model, it's the same Tory code. It just unitarily transforms into a different form, which can be defined with the spin half particles on the vertices of a square lattice. And these blue lattices are lattice plackets are actually the original plackets of correspond to the original plackets of the original deformulated Tory code. And these white plackets are those which would correspond to the stars of the original Tory code. Now, in this formulation, we will have the placket operators again for spin interactions. They will be the same for each placket, and they will be given by the products of tau y and tau z power matrices. It is a certain advantage to use this unitarily transformed Tory code, as it naturally connects to the honeycomb model as its low energy limit. But before going into the honeycomb lattice model, let me say a few more words about the Tory code itself in this formulation. We have symmetries, of course, in the Hamiltonian. You can look at the QP operators, they do commute with the Hamiltonian. So in some way they are not perhaps necessarily a complete set of symmetries, but there are symmetries of the system. So each of the energy eigenstates can be labeled by the eigenvalues of the QP operators, which are the +1 and -1. So we can label each energy eigenstate with a certain set of QP operators, QP for each placket on the square lattice. And this can be the +1 or -1. So in that way we can define a basis in terms of these symmetries, and so in terms of the set of eigenvalues of these QP operators. So in that case we have a basis which is fully characterized by the eigenvalues of the QP operators for all plackets on the lattice. Clearly the ground state, which is the ground state of the toric code in this formulation is given by the following eigenvalue equation, with all the QP's to be actually +1. So the ground state of you can say that the ground state of the toric code is defined as with a stabilizer, with a set of operators which stabilize this state. Okay, with a QP equal 1 for all the pockets. On torus, so this would be valid for plane, of course. On torus, we have to take into account one additional condition, and that's the product of all QP operators is necessarily an identity. That's simply the underlying property of the Pauli matrices. But we have to also include two additional homologically non-trivial symmetries, those which are wrap around meridian longitude of the torus. So the basis which is more suitable for torus is that one given by the original set of toric stabilizers plus two more symmetries. One can say that these are the non-trivial operations. We can say that because the Hamiltonian is a function of QP operators, the sum of the QP operators, but it's not really sum, it's not in a way related to this non-trivial homological cycles in the torus, which each can be +1 or -1. We can say that the ground state of this Hamiltonian, of these four possible values are not accounted for, is fourfold legitimate. So these are the four additional labels for the ground state of the toric code on torus. So that explains the fourfold legitimacy of the code. What about the quasi-particles? So we can talk about quasi-particles of two types in the case of the toric code. Those which are living on the plackets, which are of blue color, we can call magnetic. Those are the original, correspond to the quasi-particles on the original plackets of the toric code. So these are magnetic excitations. And those sitting on the white plackets, those would correspond to the star operators of the original toric code, are the electric charges. We can excite them by applying a single Pauli matrix on some of the vertices. We can excite them only in pairs, of course, but we can move them apart from each other without any energy cost. They are very completely deconfined particles in the case of the toric. We can also take one and move it around the other one, around a certain set of plackets. And then what such a loop does is that it measures the values of the QP operators on the opposite plackets, let's say Q electric, these four plackets, enclosed in this loop. If we have one of the plackets flipped from QP1 to QP-1, so that means we have an electric charge in this particular situation, the loop with the magnetic charge will measure it and choose the phase to -1, indicating these are relative semions. We can create a composite of two semions and we get a fermion. You can also move the fermions in pairs, but they would mutually feel with respect to other semions, either E or M particles, they would already have a statistics given by the E or M part of that composite, because M particles and M particles are mutually bosons, and E particles and E particles are mutually bosons as well. So in fact, moving fermion around, let's say, E-charged pocket can give us an information about the statistical property of that excitation, the statistical property of the braiding of the N particle and E particle, even if we move the whole fermion. That's actually quite useful in the context of the P-type Honeycomb lattice model, which I'm not going to discuss in this context much in detail. But it turns out to lead to more easy realization of braiding operations in the honeycomb, in the A phase of the honeycomb lattice model, than by directly mapping the operations from the toric code onto the honeycomb lattice. P-type honeycomb lattice model is a model with two-body interactions, which is either XX, YY, or ZZ type, depending on the orientation of the rings of the honeycomb lattice. It can be easily recast in terms of these K operators, which are simply these two-body interactions. K alpha would be simply sigma alpha sigma alpha. We will use this a little bit later, so that's why we introduced this formalism. It's known from the exact solution of the model provided by Bitayev, where he also uses fermionization of the model. It's an addition, it's fermionization into larger Hilbert space. So this can be used for freedom. Not mapped exactly into fermion units, or embedded in fermion units. In that solution, the phase A can be mapped perturbatively onto the toric code with 4 distinct particle types, as we have observed in the previous slide. It's either trivial particle, no particle, electric charge, magnetic charge, and even composite, which are fermion. It's also known to have the solution in the B phase. The B phase, if there is no external magnetic field applied, is a gapless phase. So we have a gapless phase in the central distance side, and 3 more or less equivalent of the abelian topological phases, which are equivalent to the double Z2 theory of the correspondence. If we turn on magnetic field breaks the parity and time reversal symmetry of the model, and it opens a gap in the B phase, turning the B phase actually into easing type of topological phase. This can be clearly seen in the third order perturbation theory, and was calculated by Bitayev using Charming formalism. Here, the third order perturbation theory is the leading term in the magnetic field expansion, perturbative expansion of the magnetic field. And it consists of 6 individual terms, which we will use a little bit later. So let's have a look at the abelian phase. How can be the abelian phase mapped onto the toric code? Let's assume that we have the coupling term Jz considerably stronger than J1 and Jx. This is a system with no magnetic field, so we simply make this term considerably larger. So we have strong interaction along these vertical lines, vertical edges, and we have very weak interaction, or initially no interaction, along the X and Y rings. In that case, we can initially treat the system, the bare Hamiltonian, which was given by independent pairs of spins, or each is pair of spins, and you can technically call them dimers, even though they are not really dimers. We can treat them as independent particles, whose ground state is twofold degenerate and is actually characterized by spins with ferromagnetic orientation. We can use this to define, because we are interested in low energy spectral properties of the model, we can use this to define, to look into the ground state. The ground state is this ferromagnetic configuration of of spins, and we can redefine this ferromagnetic configuration of 2 spins into effective spin up and effective spin down. So this is the ground state of this model. Then we can turn on the interaction along X ring and Y rings. So we effectively now couple these dimers And we can use the perturbation theory to look into the order expansion. What we will find is that the first non-constant term of the perturbation theory occurs in the third order, and it actually has the character of the Hamiltonian which we would expect from the toric code. So that's in the fourth order perturbation theory. The Type-Honeycomb lattice model is equivalent to the toric code with some effective interaction. Looking at the quasi-particles, just as a sort of reminder, we see that the quasi-particles in our toric code, in our honeycomb lattice model, are essentially on the same plackets from the rows of n particles and rows of p particles. Those on plackets, the magnetic charges would correspond to the original plackets of the toric code in the p-types formulation, and again the e particles will be stars in those original in that original toric code. We haven't yet talked about, we talked about quasi-particle excitations on the toric code, but we have not really discussed any excitations of the honeycomb lattice model. We have a vorticity we have a vortex operator. We can define vortex operators as a six terms on each placket. So we can already sense some analogy with the QP operators, which we have defined in the case of the toric code. We can cast them again in this language of K operators. Okay, so these would be two-body interactions actually, but their product would be simply six products of six polar matrices. This operator again commutes with the Hamiltonian. It can be easily shown through the algebraic properties of these K operators, which of course are inherited from the Pauli matrices algebra. So that's very simple to see. And then each energy eigenstate can be labeled by a certain vortex configuration. By some, let's say, a given pocket, we measure the vorticity by calculating the expectation value of the WP operation in a given eigenstate, in a given energy eigenstate of the model. If we get a +1, we have no vortex. If we get -1, we say we have a vortex. So again, the eigenvalues of the WP operator will be +1 and -1. That allows to split the Hilbert space into different vortex sectors with different configurations. We talk about vortex-free sector. We do not have any vortices. We can have different two-vortex states, the whole maze of two-vortex states, and three-vortex states, and so on. Eventually, we will come back to the full vortex sector. The Hilbert space is simply a direct product of each of these Hilbert spaces. Interestingly enough, the product of the vortex operators create larger loops. That's because of the algebraic property of the K operators, because they are just direct product of the Pauli matrices. Their square is identity. So we can create larger loops by various products of nearest neighbor WP operators, which we can cast in terms of these K operators. On the torus, there is an additional condition, which is absent in the case of the plane, and that's that once we make a product of all WP operators, we get an identity. Again, the property of the Pauli matrices. Once we start making larger and larger loops on one side of the torus from the other side of the torus, it looks like that. At some point, it starts looking like a smaller and smaller. Okay, eventually, by multiplying by the last pocket operator, we will get an identity. A good thing is that we can now study the loop symmetries on the torus, defined by these WP operators, for a system of n spins on torus. This condition implies that we really need n½ - 1 independent vortex quantum numbers to define the vorticity of different buckets. And if this would be on the plane, this would be half. Loops on torus can have the following form, and they can be either homologically trivial. So those which are homologically trivial are actually those created by products of monomials of WP operators. And then we have to add to to these n-half minus 1 independent vertex quantum numbers, or symmetries, if you want, symmetric generators, we have to add 2 additional symmetry generators, which are those non-trivial loops, homologically non-trivial cycles on those. The full loop symmetry of the torus is an abelian group with n-half plus 1 independent generators, and can be casted in the form which splits into the homologically non-trivial component, as G, and monomials of the WT operators. Now, it proves quite useful in the context of the brilliant-Wigner perturbation theory, which then allows to calculate the energy Hamiltonian for the model in the A phase to arbitrary order of the perturbation theory. And the Hamiltonian actually has a structure which reflects the structure of the symmetry. So there's a logical non-trivial component and monomials of trivial loops. As I suggested earlier, it also allows to move anyons and fermions of the abelian phase efficiently and without any extra energy costs. Because we can use these symmetries to actually move. If we do not create closed loop with the scale operators but are open loops, they would correspond to the moving of the fermion. But that fermion is actually EM composite, so it would be wrapped around an E particle that would get a semionic grading statistics. Okay, if we wrap it around N particle, we would again get semionic statistics. That's the first ideas about that are contained in this paper on topological degeneracy and vortex manipulation in the Taiwan model. There's another paper by my student Ahmed in preparation, which perhaps addresses that in more details very soon. In addition to these two results, the third result is that it allows classify completely the finite size effects, which are intrinsic to the system with the T-type Hamilton lattice system with the number of spins which is smaller than 36. In that case, at the fourth order perturbation theory, we have some of these perturbations which actually do not, some of these perturbations are trivial on the pocket operators, this one, but some of them are not trivial, they actually wrap around some of the non-trivial, homologically non-trivial cycles in torus. You can see that the original toric code, this 16 spin case, would really be just this first term. The other terms are those finite size perturbations. They are effectively seen by the system as an extra pockets, okay, which are cutting through the torus of these locations. This work was done with the student Niall Moran. He did some computational work for that, then did some perturbation theory, and it was published in Journal of Statistical Mathematics. Now, this is all about, this all was about abelian topological phase. So now, can we somehow get through? You know, so far we have relied in some extent, even beyond perturbation theory, but we relied on the perturbative mapping of the T-type Hamilton lattice model onto the toric code. That allows us to see the whole A phase, the whole abelian phase of the model, but it does not allow us to get through the phase transition into the B phase. Necessarily, we need some new idea of how to get into the B phase. And the idea comes from using an effective spins and hardcore boson representation first, and then fermionize the result of this exact mapping. Okay, so one of the big differences here is this mapping is exact. It does not use any auxiliary physical degrees of E to map our spin system into some different model. Okay. The spin hardcore bosons are defined very easily. These are possible two-spin configurations on these Z-rings. Okay, so each of these Z-rings would have this, one of these four possible configurations. And because it's bipartite lattice, we could color some of these vertices by black color, the other keep white. So we have this black and white vertices. And if the black vertex is pointing up, we say that the effective spin is pointing up. If it's pointing down, we say it's pointing down. And if the other one is ferromagnetically ordered, then we say there is no boson. And if it's anti-ferromagnetically ordered, we say there is a boson. So as we remember that when we are in the ground state of the model, we expect only this and this configuration, so only the ferromagnetic configuration. So the bosonic degrees of freedom help us to count for excitations of these dimers. Okay? In fact, what they do is they separate the degrees of freedom relevant to the toric code, those toric code stabilizers, keeping them in the place, even if we are talking about the B phase. Okay? While taking these broken dimers into the additional degrees of freedom of hardcore bosons. This idea comes from the work of Schmidt, Uzuran, and Vidal, back in 2008. The coupling terms we have in the Hamiltonian, sigma x, and so on, these Pauli operators which appear in the Hamiltonian can be translated one-to-one into the representation of spin hardcore boson language. Okay. It's sort of, you can probably see that. Okay, so let's say sigma z would be the simplest case. It really reflects on the effective spin kind of representation. Now, regarding the vortex and placket operators, in the case of the abelian phase and the perturbative limit, the fourth order perturbation theory, WQ would essentially be translated into QQ operators. There would be placket to placket operators. In the abelian phase, in the ground state. However, when we start talking about bosons, we go to higher excited states. We have to take into account also the bosonic degrees of freedom. And in this case, we get this number of operators which there is a boson in the unit particle. Okay. You can see that for in the AZ phase, we go, I should say that the description allows us to describe both abelian and non-abelian phase, of course. So in the A phase, AZ phase, JZ is much stronger than JX and JY. The bosons are energetically suppressed at low energy. The state, which would, in this new language, be described as the state of the calculation, is completely equivalent to the original toric code stabilizer. At low energy perturbative Hamiltonian, this of course equals to the toric code Hamiltonian with the identity applied on the bosonic degrees of freedom. This formulation allows us to rewrite an orthonormal basis of the full system in terms of the toric code stabilizers. So now we have the placket operators here. The logic is very much similar to what we have seen in the case of the toric code. And we have the list of those vertices, these little white boxes, in which we have some bosons. So we have a complete list of like 0 or 1. Okay? We just have the list of those which are occupied by boson. So this gives us the honeycomb placket operators, the eigenvalues of the honeycomb placket operators, measuring the vorticity of each one. And this will gives us the position of the bosons. Then, of course, if we go to torus, we have to take into account also those non-trivial symmetries into account. So we need 2 more, OX and O1, which again are in the plus or minus. Another step in our construction is Jordan-Wigner transformation. We start with this Hamiltonian in the language of bosonic and effective spin degrees of freedom. So this is just a one-to-one translation. It's an exact map of it's just exact map of the original Hamiltonian into the language of spins and bosons. But then we want to fermionize it. So we want to attach fermions to this model. And the way to do it, we can explore the string operators, which we know are fermionic operators. Okay. So in this case, we apply a single Pauli operation, excite fermions, both sides of these things, and then we move it by these K operators, which we know are symmetry, so we can move it without any energy cost. We can move the fermion without any energy cost to some point C, some vertex Q or bucket Q of our interest. And we can construct all these possible, let's say this point A would be some reference point. For each other point on the lattice, we can construct these different fermionic, these different string operators. And these string operators are really formulated in terms of the fermions, and C plus C equals SQ. There's a subtlety of there's some certain convention which we have to apply. We have to decide what the reference point is, and then we have to use the convention that the lattice which we created by the mapping onto the spin using representation. We simply start at the particular point in the lattice. Let's say it's a lower left corner, and we move first to right and then up to the desired point. It turns out that if we define the string operators in this way, we can make a one-to-one relation between this Hamiltonian and the fermionic Hamiltonian of the following form, where xq and yq are some additional quantities which actually contain these tau operators. Okay? And they are identity. We talk about yq, that's because if we are talking about interaction between, let's say, this this point on the lattice and this point on the lattice, so interaction in this edge, which would correspond to the y interaction, y interaction in the original model. And we construct two strings which overlap all the way up to this point. The product of these two segments gives us an identity, and the only thing which we are left is this interaction term, so that's why it's identity. But if we are moving, if we are looking at the interaction between these two vertices, then we have to take into account the fact that the one string does not commute with the other string, so we have this anti-commutational relation between those strings, okay, which requires to count the Placket operators vertically stacked onto this zero level. So we multiply the operators on this and this one. It's a little bit technical, but it's actually quite useful. In the case that we go into those, these y and x operators are becoming more complicated, and but allow us to really deal with the toroidal topology of the manifold on which the lattice is realized, and also allow us to deal with the vortex operators, so we can have vortex excitations. Okay. You can see that the presence of a fermion really means breaking of this anti-fermionic configuration of the Z-ring. So these are the Z-ring, and if the spins are anti-fermionic ordered, then we really talk about the fermion. We can introduce magnetic field, which is perhaps again a little bit more technical. But the magnetic field is important as it breaks polarity and time reversal symmetry, it opens the gap in the B phase and turns it into a Ising model. But fortunately, we can use just the third order perturbation expression for the magnetic field, which simplifies considerably the description because this third order correction really commutes with the Placket operator, so it allows us to use the language of the triple stabilizers. It's a little bit more difficult to construct them, but it's only possible. We can do it for all these 6 terms, and there's a rather nice graphical representation. Looking into the vortex-free sector, we would like to first go from our Hamiltonian, which we formulated 2 slides ago, this one, into the momentum representation using the Fourier transform. what we obtain in the Hamiltonian, which is already having kind of nice, concise form, with all these definitions which are given in the side. Are there any questions?
You said this magnetic field commutes with the Hamiltonian?
It commutes with the WP operators. It does not commute with the Hamiltonian.
Oh, I thought you said.
No,
Oh,
with
okay.
the WP operators.
Oh, okay.
This commutes with the placket operators. So it allows to use the torical stabilizer for noising.
Oh, okay. Oh, okay.
The effect of the magnetic field is already included. It showed up as this alpha K term, which enters delta K in these positions. The Hamiltonian in this form can be diagonalized by Bogoliubov transformation. It leads to the free fermion Hamiltonian. So this is already language, which is kind of standard, as far as I understand, standard in superconductivity. So Bogoliubov transformation allows us to formulate the Hamiltonian, which is now free fermion Hamiltonian. We'll say more about this gamma and these fermionic operators in the next few slides. And it also allows us to say what the ground state of this Hamiltonian is. And the ground state is indeed a BCS state. But because so far we have relied on the basis given by the torical stabilizers, we actually know what the vacuum on which these fermionic operators are acting is explicitly formulated in terms of the torical stabilizers. So in contrast to the previous works, which simply assume there is some vacuum, we actually do know the vacuum explicitly. So how can we use this methodology? We suddenly want to look at other vortex sectors in torus. To address arbitrary vortex configuration, we can rewrite the Hamiltonian general one into this form, into this quadratic form. And we can specify a particular vortex sector by using the operators xq and yq, which we have heard before. And on torus, we have to also include the periodicity and particularly homologic and non-trivial symmetry, which also enter into this x and y operators. In principle, what we have to do is to consider all the loop symmetries we have generated. We know that we have n half plus 1 loop symmetry generators. So we have to take all this into account on torus, of course. We have to take into account the trivial symmetries and also the non-trivial. So this square is the section of our model which is acting torus, and this would be this x chain and y chain would be non-trivial symmetries. They would correspond to minus L0 y and minus L x. Similarly, we have to include those placket operators which we have to kind of stack into each other if we talk about couplings between, let's say, these two terms, and so on. And after we do that, okay, we can come back with these quantities. We can come back to the solution of the model. So we have the general Hamiltonian in this quadratic form. We can cast this Bogoliubov-Lejeune eigenvalue problem. So taking this matrix, we can split it into 3 distinct terms. And then we can express this Hamiltonian in terms of the quasi-particle, in terms of the fermions, gamma plus and gamma, which very naturally appear from the spectral multiplies UV star matrix of this block. Then we have a diagonal term, UV star dagger is in column. Okay, so this is the definition of the gamma dagger and gamma. And this Hamiltonian has the eigenstates, which are the same form as we have seen in the vortex free sector, except that here we don't only have all QQ equal 1, but we have 1 and minus 1 possibly, and we may have some bosonic excitations as well. Actually, sorry, in the case of the ground state, we do not have the bosonic excitations. We have only various vortex sectors, ground states. Now, what about the momentum representation? So we can transform the system into momentum representation. We have to take into account, because it's on torus, we have to take into account the periodicity of the momentum. In that case, we have this extra factor theta alpha, which corresponds to, which reflects the non-trivial symmetries. It's really a momentum shift due to the going around the torus. And in fact, only for the configuration minus minus, that means we have those four symmetries where we can have plus or minus 1 for L0, X, or 0, Y. Only the configuration minus 1 is fully periodic, so it becomes 0. We have K alpha equals to pi alpha divided by capital M alpha. And that permits the momenta of pi exactly. Now what that means is that in this particular symmetry configuration, the delta pi becomes 0. Psi pi over E pi is actually minus 1. It changes the sign and then goes to minus 1. That implies that U term is becoming 0. V term is becoming just imaginary unit. Okay? And in our ground state, this term is 0. It's a product, so this term completely, the state with the pi, with this symmetry is having 0 component here. It's having 1 for Vk, or I for Vk, but Ck dagger becomes C pi, and C minus K dagger becomes C pi as well, because of the periodicity. And that really means that we have 0 here as well due to the Pauli exclusion principle. So in fact, one of these BCA states, originally we had 4 of them, because we had 4 distinct BCA states for those non-trivial, homological non-trivial symmetries. Now one of these 4 states, and only this one with this particular symmetric properties, is annihilated, disappears, if we cross the phase transition from the A phase to the B phase. So this is really valid for the B phase. Okay, once we cross the phase transition, this term changes the sign and annihilates this particular state. So we can conclude that the ground state of the system in the non-obedient phase intervals is threefold degenerate as expected from the reason theory. And to somewhat maybe more surprising statement is we have these 4 BCS states in the middle in the A phase. One of these BCS states, when we cross the phase transition into the B phase, is annihilated. We are left with a threefold ground state given by the BCS different symmetries. Okay. Let me just conclude briefly. We have a closed expression for the ground state of the Kitaev-Hamilton lattice model, where we exactly know this vacuum state. It's a ground state of the toric float. The description we have combines 2 powerful wave function descriptions, the BCS product, or I should say also Hartree for the Ribov theory, and stabilizer formalism, this connection with the superconductor, which is very obvious, very manifest in this case. It shows the relations between the double Z2 abelian phase of the toric code and the easing on abelian phase in terms of these BCS states. Okay? It explains the ground state degeneracy of torus, and actually it also explains its change once you go from the A phase to the B phase, and the phase transition between A phase and B phase. And it also allows us, at least in principle, though technically this may be harder, to calculate the ground state of any vortex configuration in torus, and things which I have not talked about, which are in progress, are perhaps generalization of this technology for Yao chaos and black models, which we are in the process of establishing recently. And I will stop at this point. Thank you very much.
We have ample time for questions and remarks.
Yes, something I didn't understand. When you did this fertilization, you started you had an Hamiltonian that spin tau operators and d operators, and then you bosonized the boson, what happened to the spins?
So the spins are still there, right? This is an exact mapping. We have 4 states here on the left side and 4 states on the right side.
Yeah, that
They
part.
carry the information about the spins, and they become tau and b. They become related to the spin
Yeah.
degrees of freedom are reflected by the Pauli matrices, which we call tau, which are Pauli matrices acting on the effective spins. Okay, so the tau are Pauli matrices acting on this basis on the effective spins, and the b are really the bosonic.
Yes, but that raises the next step.
So we have them still contained in this expression.
Yes.
And after we fermionize, you can see that if I look at the right hand side of this SQ prime, which is the same as this string operator, except the last, which is the last term, which is the bosonic degree of freedom of the last vertex. Okay, that's taken out. So we keep that as BQ. So all that chain of bosonic and spin degrees of freedom is contained in the string operator. Okay. And that becomes part of this WQ operator. So it actually is contained in this XQ.
So it's too naive to think of having. I thought of that you had 1 degree of freedom, that you had it, each.
It's exact mapping. It's for each spin we have, for each pair of spins.
Is it?
4 spins.
Well, maybe
Maybe if you
Yeah.
can comment on that.
the kind of miracle that happens is that, of course, you have a dependence on all those tau operators,
Yeah.
even in the final Hamiltonian. But it's all contained in those x and y operators that appear there. And the nice thing is that the x and y operators only can be written completely in terms of the vortex operators of the model. So with your symmetry, so you can just fix them for any sector and then they become constants.
Okay.
So
Okay.
so once you do that, then it's fall out.
And then it
What is
becomes
the-
And this is
fermionic.
because you choose the
Okay.
strings in the right way.
Right. All these WQ operators are symmetries.
So the choice was important.
Yeah, so
Yeah,
important
well,
thing is
you very likely can make a different choice, which works as well.
but it really doesn't matter really how the string is oriented on the lattice or anything, but you have to use
You have to use the same for all.
the symmetry operators of the model base.
It's I understand part of it is maybe technical.
Or you get all the endpoints on the spin to be on the lattice and not on the line.
You get all of them, right? Because you have those strings here go in 2 different directions. That's to this path. So any point on the lattice can be some sequence
To the right and
of
the
steps to the left and to the up.
and you get fermions.
Yeah. That's actually, I guess. In fact, you get fermions are contained in this SQ prime. You can show, for instance, that they have anti-commutation relations because the proper anti-commutation relations. They actually do commute everywhere except if I have 2 such fermionic strings, I start here and go up here, and I start here and go up here. They actually have anti-commutation relation in this point. The properties of the matrices. Those original chains. So yeah, it's quite, I would say it's very clever. So it's spectacular. Okay.
More questions?
So, can you now use this to calculate interesting correlation?
Oh, we haven't. We can calculate things which are. We calculate a number of things. The first thing to calculate is to look at the properties of the ground speed and toes. So naturally, that's our major. It was our first interest. Basically, try to see. That this is the first result. Try to see really what the ground try to see the phase transition actually in that description. Because obviously the BCS states, the ground states and torus, are there all the time. But once you go from the A phase to B phase, instead of 4, which you would expect from the symmetric properties, you get 3, because one of them is annihilated with this mechanism described here. So that's, you can say this is one of the first applications, highly trivial applications. You can use it computationally. I did not say that, but you can, and actually you can compute, for instance, gap in various systems with the sizes which are astonishingly large. Like, really, we have done like absolutely standard computations, which we do now on desktop. It's like 80 by 80 spins. It's kind of breathtaking. It's for me because it's been lots of time super computer. So it's it's huge. I mean, it's very big potential. Suddenly we can apply it in other models, which we think we have explored it in some extent in the context of the kilosons models. We have basically the same properties. You can use the same technology in the context of the kilosons models, which is nice. And possibly one of the non-trivial directions would be to try to find other models with the same properties, which possibly could be realized more easily, which we of course are working on, thinking looking. Yes.
And maybe one other point is with the stress on this slide actually, so you can easily calculate the spectrum
You
for
can.
arbitrary vortex configurations.
Yeah, absolutely.
So
Yeah, all this, in some way, I think you can get arbitrary vortex configuration, you can do it on torus, you can do it on plane. You can do it with different plugins, and this kind of diamond plugins, which are more natural if you define the unit vectors in the way we did in this particular work. But you can also do a square lattice kind of acting torus. So that's sort of different configuration of different. There's no different topology in the manifold. It's flat, so you have plane. It's a honeycomb lattice. You can have torus, but suddenly the explicit ground state is nice. You really know what you are applying those operators on. There's lots of connections with the works on potential connections with the works on, let's say, music with reading green and flight off state. Connection with the PAs, of course, very explicitly.
You mentioned you had 4 degenerate states, which the phase transition turned into 3. What happened to the 4th state?
It annihilates.
It cannot disappear.
It's the ground state, it can disappear.
Well, the piece is so is one.
It annihilates. It
Other
becomes
state.
zero. It becomes zero.
Zero back and
Because the product is overall momentum, the last term, the vast momentum is really pi pi.
It's not that it splits up.
If you want me to, like this, it's actually probably can be seen. If kx and ky are pi, then delta k, alpha k and beta k, which enters delta k. These are sine functions, right? So if the momentum is pi, then delta k becomes 0. Okay. In the non-abelian sector of the non-abelian phase, this becomes -1. It's because delta k is 0, you really get psi k is changing the sign. Okay, because of these cosine terms. So psi k is changing the sign. Divided by ek, which is implied pi, it becomes -1. And if you look at uk and vk, and you get uk equals 0 and vk equals I, vk has two creation operators with the same momentum. So that's the definition. uk is 0 and this term is 0 as well.
Yeah, that's
So it really is annihilation of the third sorry, it's annihilation of the fourth PCS state. Once you cross the phase transition, one of these states vanishes.
So that then another
And
state is created
says on
somewhere?
that.
Another state in the spectrum is created all of a sudden somewhere? Or?
Disappear.
The open space state
There's-
there is a ground state in that symmetry sector, of course, that has higher energy.
I would have expected there was one state that splits off, and it's not the ground state, then
Yeah, I think there's a point about it in the Reed and Green's work,
Yeah.
I think which really means that one of
Yeah.
these is in fact a lifted up in energy. So
Yeah.
it's not anymore in the
Yeah,
ground
yeah,
state. So it's not ground state, it becomes a different state. It doesn't vanish in that respect. It's annihilated in the ground state.
Okay, more questions or comments?
Because I should maybe point out, this does not describe the whole Hilbert space, okay? This describes the ground state with the zero bosonic excitations. So you have excitations to go.
Okay, it's time for coffee,
And
and
perhaps I should say one more thing. And that's that I'm casting my postdoc till summer of fall of 2010. And because you are all friends, I should tell you that he will be available maybe for another postdoctoral position sometime next summer or early fall.